Hey guys, so we're going to go ahead and just quickly finish up the solution to the problem we left off in class with. So we talked about how we can solve projectile motion, and one of the basic strategies is typically, since you have two directions, a y and an x, you'll end up with a system of equations, meaning two equations, two unknowns. One of the unknowns is almost always time, and you're going to solve for time in one of the equation, either x or y, and then end up plugging it back in to the other one to figure out what you're really looking for. So we looked at first an example where we used the x direction to solve for the time, and then plug that into the y direction to find the height. And then we've been looking at two examples here where we actually had to use the y direction, which turned out to be a quadratic if the initial y velocity isn't 0. And that means we're going to get an answer with two solutions. Pick the solution that's not negative, plug that back into our x direction to find delta x or the range. So here we did that, and in class we left off with this quadratic here. So this quadratic yielded two solutions, a negative and a positive. Obviously we're going to want to pick the positive time because the negative time we know is impossible. We're going to plug that into our x direction equation here, where we have the component or the x component velocity from what we found earlier, and we get that the projectile goes about 0.15 meters. All right, that's all good. Now, there's two more styles of projectile motion problems that you may commonly see, and they involve the use of what is known as a range equation. So a common scenario or a common question is something like this that you could see on AP. It asks to derive an equation for the range of the football. So when we talk about range, we're talking about the horizontal distance covered in terms of the initial velocity v0, which is punted g, and the angle theta. Which angle would produce the greatest range? And so this football player is going to kick it at a bunch of different angles, and after we derive an expression, we want to ultimately come out and figure out which one would be the greatest. Well, so the situation that we ultimately have is this one here. We have the projectile starting and landing at similar heights, or rather the same height. It's given some kick at an initial velocity 0 at some angle theta. It's going to hit a max height before falling back down and hitting the ground with some final velocity vf at some time t. Now, the problem doesn't discuss it, but I do actually want to draw a couple important things that can be later used to solve other projectile motion equations. And that is what happens here when the ball reaches its max height or its peak. Well, very important thing here is that the peak is actually what's happening to its y velocity. So to illustrate that, I'm actually going to draw a couple different points on here. Well, we know that the only force accelerating it is the force of gravity acting downward. So as it's going up, its velocity is upward in the y direction, and its acceleration is downward. So that means as it's decelerating, right? The signs of the velocity is positive, signs of acceleration is negative. So it's going to start with some really high and y velocity, and that velocity is going to have to decrease over time. And then when it hits its peak, it's going to stop moving upwards and start moving downwards. So that means at the peak, its velocity in the y direction is 0 meters per second. And that's something very important to realize. Anytime a projectile reaches its max height, its y velocity is always 0. Then on the way down, its velocity is now downward, and the acceleration is downward, meaning it's going to start accelerating here. Well, what about the x velocity? Is the x velocity also 0 at the top? Well, we know that for a projectile, there's no force in the x or the y direction. So as soon as it becomes a projectile, it's there's no force in the x direction, going left or right. So that means its x velocity is actually constant the entire time. So it's got the same x velocity no matter what, which is exactly equal to its starting x velocity. So that's pretty interesting. So, but here, our x velocities are initial x velocity, meaning it can't be 0. And as long as they're landing and starting and landing at the same height, it also gives us that the initial velocity and final velocity are actually equal, but the signs are going to be different. So in this case, the x velocity is the same, but the y direction velocity has changed its sign. Now, what do we know? Well, I definitely know that acceleration AY is g. So they've asked us to find g. They're using g as acceleration due to gravity, theta, and the initial velocity v0. So I can only have those terms in my answer. I know the time of this event, we're just going to call t. Well, I don't know anything, I'm not given anything about v0x or v0y, but I can break this thing down because here I would have some v0x, and then here I would have some v0y. So that means v0x would be v0 cosine theta because it's adjacent, and v0y would be v0 sine of theta. And I also know that delta y is going to be 0 because it's starting and landing at the same height. Well, I want to derive an equation for its range. Delta x equals v0x times t, or delta x is equal to v0 cosine theta times t. Now the problem is I don't want to have t in my answer here, so I'm going to have to pick a y direction equation and solve for time, and then plug it back into my x direction equation to eliminate it. Well, for my y variables, I have v0y, delta y, and ay. So I don't have v final y, and I want to solve for t. So I want to get rid of any equation with v final y. The only equation that doesn't have v final y would be this one here. All right, so I'm going to go ahead and plug some things in. So we have 0 equals v0 sine theta. I forgot the t, sorry about that. Plus 1/2 g t squared. Okay, well, let's see. If I subtract v0 to the other side, equals then I see that actually a t squared and a t canceled, and that only works because I have 0 on this side. If that side wasn't equal to 0, this would cause problems. And let's see. So we have negative v0 sine theta is equal to 1/2 gt, or in this case I get that t is negative v0 sine theta, and I multiply both sides by 2, so I get a negative 2 on the top over g. And I can take that and plug that back in. So now I can say, well, delta x equals v0 cosine theta times, now my value for t, which is negative 2 v0 sine theta over g. Or I have delta x equals, let's see, 2v0 negative 2v0 sine theta, and that's squared cosine theta over g. Now, it's kind of hard to see, well, looking at this, what angle would produce the greatest range or the greatest delta x, because I am trying to essentially here maximize sine of theta and cosine theta. Now, you don't really have to know this identity, and after we derive it, it's not used a whole lot, But if you recall from math class, you actually have that 2 sine theta cosine theta, and I'm going to move that over just a little, is actually equal to sine of 2 theta. So I have 2 sine theta cosine theta, and I can substitute this in. So moving on to the next slide, I left off with delta x equals negative 2v0 squared sine theta cosine theta over g, or that delta x is equal to, with our substitution or trig identity, we have v0 squared sine 2 theta over g, where we're saying that g is equal to negative 9.81 in here, so those the negative from this g and this would cancel out. So I'm going to say so we know that those negatives go away. And what I can see here is that now, in order to optimize this range, I have accomplished my goal. I only have v0, theta, and g. And if I want to optimize this range, I must so I just need to figure out when sine is going to be the greatest. So sine is the greatest when it's 90 degrees. So in order for make this to be 90, or sine of 90 degrees is the maximum value of 1. So here, that theta must be 45 degrees. As if it's 45 degrees, I'll get 90 in here, and I'll maximize this range. So, interestingly enough, if you want something to go to the farthest it possibly can, not necessarily the maximum height, but the furthest possible, you would want to fire or kick that projectile at 45 degrees. Now, this equation here is known as the range equation. This is not on the AP formula sheet, but it is a rather helpful formula. However, it only works for objects launched and landing at the same height. It is fairly helpful because often you can use this range equation for this specific scenario to go through a couple multiple choice questions rather quickly, rather than trying to derive this equation mid-exam and then use it to solve what is supposed to be a 30-second multiple choice question. So it is helpful to memorize this equation, know what it's doing, and then know when is appropriate to use it. I'm also going to post another link to a video showing you how to use the range equation or derive a more general one